The CMB and the Early Universe. This is the title of the next part of this event. And so I thought for that I would show you a map of the CMB. This is a map of the afterglow that comes from the Big Bang. And this is showing the temperature fluctuations of this light that comes from the Big Bang. And by studying the statistical properties of these temperature fluctuations of the photons that are coming from the Big Bang, we can learn about the physics from the very early universe, about the composition of the universe, how much dark matter there is, how much dark energy there is, and how much ordinary matter we have. So, at the very beginning of the universe, it all began by a hot and dense plasma of particles in thermal equilibrium. And as the universe expanded, it cooled, and many different physical processes happened. Some of them we don't know the physics, and some of them we know very well. So we know that 380,000 years after, light years after the Big Bang, the universe had reached the temperature that it needed in order for the protons and electrons that were around to form hydrogen atoms. So at the very beginning, before this period, protons, electrons, photons, the light, was all together. It was like a fluid oscillating together. The protons and electrons wanted to go down a potential formed by dark matter, and the pressure that the light, these photons exerted, wanted them to go out. So the fluid was going into gravitational potentials and out of gravitational potentials, in and out. And these are the sound waves, the cosmic symphony of the very early universe. When the universe was 380,000 years old, protons and electrons combined into hydrogen atoms. The temperatures were enough for this to happen, and the universe became neutral. So since then, the photons came toward us almost conserving entirely this information. So that's why when we look at a map like this, we can think of it as a snapshot of the very early universe, a snapshot of the time in which the universe was behaving as a fluid of protons, electrons, and photons. And by measuring the statistical properties of these temperature fluctuations, we can learn, looking at this sequence of peaks that describe, for example, the power spectrum, the square amplitude of these temperature fluctuations, we can learn how much protons and electrons there were, how much dark matter there is by measuring the amplitude of these peaks, by measuring the position of this peak, the angular position of these peaks. We can measure how much, what was the geometry, what is the geometry of the universe, how much dark energy there is. And by measuring how these peaks are tilted, we can also learn about the physics of the very early universe, what was happening back at the very fraction of a second after the Big Bang.